Alright, welcome to video presentation number 2 for ME360, and let's get right into it. Water enters a radial turbine at a 25-degree angle from a line tangent to the outer edges shown here. Blade angles are as indicated in the diagram, and the blade thickness is 20 centimeters throughout. If the turbine operates ideally, what will the power output be when the flow rate is 10 meters cubed per second and rotational speed is 80 RPM? Automatically, we know rotations per minute is whack, so we need to change this to radians per second. So 80 rotations per 1 minute. We know that in one rotation there is 2 pi radians, and we know that in 1 minute there are 60 seconds. So we have 80 times 2 pi divided by 60, 8.37, we'll call it 8.378, 8.378 radians per second. And that was step number 1. Okay, so step number 2 is to draw the inlet and outlet vector triangles. So let's go ahead and do that. Is this, yeah, okay. So we'll do the inlet first. So let's say, pretend we move this so that this is horizontal to you guys. Maybe not, that's more like it, but yeah, pretend that's what we did. So we would have a U that is horizontal here. So these are called 2 and these are called 1. This is called VR2, but it should be called W2. This is called VR1, this should be called W1. W1 and W2 are the velocities of the fluid with respect to the blade, and V is just the absolute velocity of the blade. So let's go ahead and draw these triangles. Like we said, this is U. So this is U, that means that W2 creates a 145-degree angle. How did I get 145? Well, if you see, this is U, this is W. If this creates a, sorry, not 145. So this creates a 60-degree angle here. That means that this here has to be 180 minus 60, which is 130. So this creates a 130-degree angle. So this is U2 here. That means that W2 creates a 130-degree angle here. And V2 creates a 25-degree angle. Once again, we have a horizontal. We have 25. That means that this is 25 as well. So here's our V2, W2, 25 degrees. Okay, so we're trying to find power, and in the power equation, which I can write now. Power is equal to torque times the rotational velocity, which is also equal to rho Q times V theta 2 times U2 minus V theta 1 times U1. V theta 1 is the component of the absolute velocity that is along the tangential direction, which is coincidentally the U2 direction. So what we need to do is break down V2 into components. One in the tangential direction and one in the radial direction. So if this is V2, it means it has a V theta 2 and a V R2, and this is a 25-degree angle. And if you notice, we can define V theta 2 in terms of VR2. The reason we want to do this is because let's say we zoomed into this spot here, and this is what it looks like, the inlet. So if we have a tangential direction at this point here, that means that the radial direction can be found from the flow rate. This velocity has to do with the flow rate. I'll show you how to do that in the next few steps. So let's go ahead and define V theta 2 in terms of VR2. So V theta 2 is equal to VR2 times the cotangent of 25 degrees. Cotangent, if tangent is opposite over adjacent, cotangent is adjacent over opposite. So the cotangent of 25 is the, we can do the trig elsewhere, so let's do it here. Cotangent of 25 degrees is equal to adjacent over opposite. Adjacent is V theta 2 over VR2. This is just basic trig. Move this to the side and you have this equation. So we have one part of this done. We have rho, the rho is just going to be 1,000 kilograms per meter cubed. Q is the flow rate, which is given here. So we have 3 parts to our power equation now. Next up, we have to find the outlet V theta 2, or the outlet tangential component of the absolute velocity. Let's analyze this outlet now. The outlet triangle, vector triangle. So this is what we have at the outlet. Once again, let's pretend that it goes straight across, which it does in this case. The blade velocity, U is the blade velocity. If I did not mention before, U is the blade velocity. So here we have U1, and then this is like the radial direction, the radial axis, and we know that W1 is 30 degree, or makes a 30-degree angle with that axis. So this is W1, this is 30 degrees. And then, so, oh, sorry, I didn't mention that from dynamics, we know that V is equal to U times W. So V1, or in this case, V2 is equal to U2 plus, sorry, not times W2. So we know this from dynamics. Therefore, that's why I did these two first and then you sum it. Here we do these two first and then we sum it. This is V1. So just like we did with this one, we broke this down into components. We need to break this down into components, or at least the absolute velocity, V1. It's going to have a component in the tangential direction, V theta 1, and a component in the radial direction, or normal. It's also known, the radial direction is also known as normal. I use the names interchangeably. Just know that when I say radial, it means the normal direction. VR1. So once again, we want to define V theta in terms of VR, because we can find VR from the flow rate and the area of this blade, or blade. therefore, or the blade, or the area of the outlet. So if you notice, if this entire, I'll do this in a different color. If this entire vector here is u1, and we break this down into components, this here is br1, and this here is b theta 1. That means that we can find b theta 1 by doing u1 minus, or b theta 1 is equal to u1 minus this length here, and we'll just call it L. So we need to find what L is, and we know that this is also VR1 here, and this is also L here, because it's a square or rectangle. And we know the degrees here, or I mean, we know the angle here. Therefore, we can use this angle to solve for L. And we'll do another trig tutorial here. Tangent of 30 degrees is equal to TOA opposite over adjacent. Opposite of 30 degrees in this case is L. Adjacent is VR1. Multiply it over, and then L is equal to this. So, or once you move it over, so VR1 times tangent of 30 degrees. This being L. So we have now defined our tangential components of the absolute velocity in terms of the radial velocities. So, and the blade velocities in this case. We also know that u, the blade speed, is just a tangential speed, or tangential velocity. So we know that u1 is equal to r1, omega times r1. We found omega up here in terms of in radians per second. So this is just going to be 8.378 radians per second times r1, which is shown here, 0.8 meters. So u1, we can find a value for u1. That is going to be this value times 0.8, and it is, I should have done this in a different step because we also need U2, but here we are, 6.702 radians times meter per second is U1. U2, you guessed it, is omega times R2. Omega is the same no matter where you are on the radius. Once again, 8.378 radians per second multiplied by R2, which is 1.2. These are all the 2's, so R2 is 1.2 meters. This is equal to 10.05. 10.053 radians times meters per second. All right, so now we have U2, we have U1, and we have these defined in terms of VR1 and VR2. So the next step is to find actual values for VR1 and VR2, but we can just plug into the equation as is. Power is equal to rho, we'll do variables, rho q times v theta 2 which is here, BR2, cotangent of 25 degrees, times U2 minus V theta 1, which is this whole value here, U1 minus VR1 times tangent 30 degrees. This is multiplied by U1, the blade speed at the outlet. And there you have it. So now, I just wanted to have this in terms of variables. We should find values for VR1 and VR2. So let's do that. VR2. Can you guys see this? I hope so. My phone is running out of battery, but sorry for the brief intermission as I do this. Okay, back to here. I hope that didn't mess anything up, but you can see the work. I hope that did not mess anything up. Anyways, so we need to find values for VR2 and VR1. We find that from the flow rate. So this is going to be Q over area 2, and this is going to be Q over area 1, because Q is equal to V times A, velocity times area. So now the areas is something that we have to look at. So Q we know is 10 meters cubed per second over area 2. So area 2, to find the area of a cylinder, you multiply the circumference by the thickness of the cylinder, because it's really just a big rectangle. Circumference of a circle is 2 pi r. So for A2, 2 pi r is going to be 1.2. And so 2 pi r, and then times the thickness, which is 20 centimeters, which is 0.2 meters. Same thing here for the outlet, meters cubed per second over the circumference, which is 2 pi r. In this case, the R1 is 0.8 meters, and then times the same thickness, which is 0.2 meters. So for the first one, 10 divided by 2 pi times 1.2 times 0.2. 6.63 meters per second. And then here, 10 divided by 2 pi times 0.8 times 0.2, 9.947 meters per second. Okay, now that we have values for VR1 and VR2, which are the tangential components of the velocities, we can plug them in here where not tangential, radial / normal, whatever you want to call them. Plug these into the power equation, and I'm gonna now use numbers. So power is equal to 1,000 kilograms per meter cubed times 10 meters cubed per second. Can you guys see this? Yes. Times VR2, which is 6.63, times cotangent of 25 degrees, times U2, which we already found value for, 10.053, radian meters per second. We'll do it. This is meters per second, and this is radians times meter per second. Boom. This is all minus. I'm going to draw it down here. U1, which is 6.07 or 6.702 radians times meter per second, times this big equation, or no, sorry, minus, yeah, VR1, 9 point, yeah, you guys can see this right here. I'm just plugging in values for this. Minus 9.947 meters per second, times the tangent of 30 degrees. This is once again times U1, which is here 6.702 radians times meter per second. All right. Unfortunately, I did not calculate this beforehand, so let's get to that. So we'll do this side of the equation first, times tangent of 30 times 6.702. So this is going to give you a 38.49 over here. And we do 6.702 minus that value. Is that the case? We have double subtraction here? Yes, we do have double subtraction. That's okay. So 6.702 minus this value. So here we have a value of minus 31.787. And then we're going to subtract this value, so it's actually positive. But first we need to find this value here, which is 6.63. Let's go back and find 6.63, boom, times the cotangent. That's arctangent, snap. 1 second while I calculate this using my phone, which is not available because I'm recording with it. Computer. Cotangent. Okay, so it's 1 over tangent of 25 degrees. Boom. So we now have 14 point on this side. Oops. So that's just this value. We need to multiply it by 10.053, which is here. So we have 142 value, 0.96. I'm keeping all the float in the calculator. I hope you guys can see that. So we do this, minus, homie. That makes sense, yeah. So in our bracket, so now we have 1,000 kilograms per meter cubed times 10 meters cubed per second times 174.75. We'll call it 17.76. So now we just multiply by 10, multiply by 1,000. And here's our value in joules. We have to keep in mind that this is all meters and kilograms. So it's going to be in joules. So to convert this to kilowatts, or I'm sorry, it's going to be in watts. This is going to give you a watts. So to convert to kilowatts, we just multiply by 10 to the minus 3. So 1, 2, 3. So the power is equal to times 10 to the minus 3. 1,747.55 kilowatts. And that is your answer. Be the power input. Yeah, power input would be 1747.55 kilowatts. Thanks for watching.